Hello everyone. The topic we are going to take today is the external flow. Up till now, we have completed the internal flow. When the flow is within the pipeline or within the surface of the body, it is refers to as internal flow. But now, as the name indicate, if we are talking about a flow which is taking place external to the surface, which is taking place outside the surface of the body, which we are considering, then it is refers to as external flow. Extremely important topic, and many of the times questions are asked in gate from the boundary layer theory. We will be understanding what is actually the boundary layer, the concept of boundary layer, and what are the various region we need to consider while applying the boundary layer theory. This is simply an introductory video to give you an understanding about the boundary layer. All right, so let's start. The topic is also important because it has a wide application in the industrial field also, such as the flying of an aeroplane. What are the forces acting on an aeroplane? You know? So the concept is extremely important. So do listen to it. So let's start with the introduction. Boundary layer concept was first introduced by Prandtl in 1904. So what actually is boundary layer? Let us understand. Suppose this is a surface, this is a solid body. All right. A body can be, you can consider as a part of a solid body, such as an aeroplane, which is flying in air. So basically, this is a solid body. What happening is a fluid is flowing in this direction. This is a large amount of fluid up to higher level. This is the fluid flowing on this solid body. This is solid body. All right. So what happening is the part of the fluid when it this part of the fluid when it comes in contact with this solid body, the surface. This is the surface of the solid body. In fluid, in the internal flow, we were dealing inside the pipe, inside the pipeline. But here, this is the surface of the solid body. This is the external surface. So the part of the fluid at this point, suppose what happens is this when this reaches this point, so basically at this point the velocity, some of the particles of the fluid, whether it may be air or water whatsoever, the velocity will be zero at this point, because the layer which is in contact with this fluid get stick to it. We assume it that it sticks to the surface. So the velocity at this point is zero. This is also known as no slip point. And as we move upward, the velocity gradually increases. So here the velocity is zero. As we proceed upward, this velocity keeps on increasing. So if you see the basically the trajectory, you will see like this. So this is basically the concept of boundary layer. And what is the boundary layer? Boundary layer is nothing but this dale. This is the boundary layer thickness. up up to the height, up to what height the boundary layer is formed is basically what boundary layer thickness. And the velocity, this is the velocity graph which is shown at the surface of this solid boundary. The velocity will be zero because few of the particles will be sticking to this surface, and as we proceed upwards, the velocity keeps on increasing. So, in the immediate vicinity of the boundary surface, the velocity of the fluid increases gradually from zero at boundary surface to the free stream velocity. What is free stream velocity? The velocity with which this fluid is flowing is u infinity, which is refers to as free stream velocity. This is the velocity which the fluid is flowing. All right. So basically, at this point, the velocity is zero, but as we proceed upward, at this point, as the boundary layer thickness increases, at the uppermost layer, the velocity reaches u infinity. So basically, suppose, understand by this diagram, suppose this is the free stream velocity which is occurring at 10 meter per second. This is the solid boundary which you have, all right. And at this point, the velocity is zero. This is the no slip condition. And as we proceed upwards, you can see it's 2 meter per second, then 4, then 6, and eventually it's 10 meter per second. Sorry. So basically what happening is, at the top of the boundary layer, the velocity reaches 10 meter per second and it increases gradually. So the graph follows like this pattern in the boundary layer. Alright, this is refers to as leading edge, the edge in which the which is the start of the solid surface, and this will be the trailing edge. This is the trailing edge or the end part of the, alright. And the point at which the velocity is zero is refers to as no slip point, or the point at stagnation point at which the velocity is zero. All right. So basically, how this graph is drawn, this one graph is drawn. For example, if we consider, let us suppose the entire length, of this plate is suppose L, and suppose we start at x distance from this side. At this point, x is equal to 0, and at this point, x is equal to L. So if we take various point at this surface of the body and we draw this graph, suppose here, here also it will follow the same similar pattern, like this. Similarly here also it will follow the same pattern. So basically at the uppermost portion, the velocity reach will be what? Free stream velocity, that is u infinity. Here also u infinity. Here also here also u infinity. So if we join the various point on the boundary layer at the location, at different location at x, x, x and x, if we join the various point on the boundary layer at which the velocity reach is u infinity or the free stream velocity, and we join all these point, we get this graph, this basically this curve. This is the curve, this is the point. At this point where velocity is free stream velocity, this point, at this point where velocity is free stream velocity, and if we join various point on the boundary layer surface at which the velocity we receive is u infinity, this curve if we join, then we receive the boundary layer graph. This is the boundary layer. This is basically the imaginary boundary. This is the imaginary boundary which we are considering, and various questions are solved on this concept only. So at this location, this is the boundary layer thickness. At this location, this is the boundary layer thickness del. So you can see from the graph, as we proceed upward, at this position it's del, then finally del increases, finally del increases and increases. So you can see as we proceed towards the trailing edge, from leading edge towards the trailing edge, the boundary layer thickness basically increases. I hope this is clear. And the points, these are the points. If we join the points on the various, by considering the solid body at different location on the solid body, if we join the points of the free stream velocity, then the trajectory we receive is this boundary layer graph. This boundary layer. So this is simply the boundary layer concept. All right. So you can see when a fluid flows past a solid body, the fluid particles adhere to the boundary and the condition of no slip occurs. All right. When the fluid flows, as I told you, some of the fluid particles stick to the surface of the solid boundary, and at the velocity at which there is zero velocity, this is the no slip condition. no slip condition, you can see it means the velocity of the fluid at the boundaries at the body surface will be same as that of the velocity of the body. Secondly, one more thing. One more thing is that uh, within the boundary layer, within the within this region, within the boundary layer, within this region, basically there is a friction, there is the shear stresses which are acting because the fluid has some relative velocity. You can see there is relative velocity. This is 2 meter per second. Then this is 4 meter per second, then this is 6 meter, then 10 meters. So there is a relative velocity within the boundary layer. And once this is reaches this point, this is the velocity of u infinity. And up to higher point, up to this point also, it's u infinity. This is also u infinity. So there is no relative motion outside the boundary layer. So basically, there is no shear stresses which are acting at this region. They are only shear stresses acting in the boundary layer. I hope this is clear. So basically, we can use, and as we know, the Bernoulli equation which we derived earlier is basically the defined for the ideal flow. Ideal flow when there is no shear stresses acting, when there is no surface tension, the fluid is ideal. There is no viscosity. All right, but there is also the viscosity because there is a relative motion between the layers of this fluid and there is no relative velocity. So the Bernoulli equation can only be applied at this point, only in this region. So Bernoulli equation can only be applied outside the boundary layer. Remember this. This was asked in the previous year gate question. Bernoulli equation can be applied only in this region. In this region, within the boundary layer, since the fluid is having relative motion with respect to their own layers and there are shear stress acting, they will Bernoulli equation cannot be applied in this region. In this region, there will be no application of the Bernoulli equation because the Bernoulli equation is only applicable in case of ideal flow. I hope this is clear. Right. So you can see outside the boundary layer, effect of shear stress is very low. There is effect of shear stresses, but it is very low that we can neglect it. And the velocity gradient is negligible. Velocity gradient, what is velocity gradient? Velocity gradient is du by dy. This you might have studied in the uh, properties of fluid. Shear stress is defined as mu, which is coefficient of viscosity, into du by dy. So basically what is happening is, due to this velocity gradient in the boundary layer, there are shear stress acting. All right, you can see due to these velocity gradient, this change in del as we proceed upward, this change in velocity. So basically, there is du by dy which is existing within this zone. So due to this reason, there will be shear stress which is acting due to velocity gradient. So there are shear stress acting in this zone, due to which we there's shear stress acting. But if you see in this region, there is a velocity of u infinity. At this point also there is u infinity. At this point also there is u infinity. So the fluid outside the boundary layer, the velocity gradient du by dy is zero because there is no change in velocity with respect to the y direction. So there is no relative velocity in this region outside the boundary layer. So basically, the shear stress, since shear stress is tau mu du by dy, since this portion is zero, therefore shear stress is also zero. Where? In this region. I hope this is clear. So basically, the Bernoulli equation can be applied only outside the boundary layer. Why? Because there is no velocity gradient, there are no shear stresses, and the fluid flow outside the boundary layer can be considered as the ideal. While within the boundary layer, there's a relative motion and there's a velocity gradient. All right, due to which there are shear stress acting. That is the reason we cannot apply Bernoulli equation within the boundary layer. All right. So our course of study is only applied to this region only, because we need to see what are the forces, what are the stresses, what are the shear stresses, what are the velocity gradient which are acting within this zone. So our area is confined to this region only. I hope this is clear. So you can see, note, Bernoulli equation can be applied outside the boundary layer. Why? Because there are no shear stresses, there is no velocity gradient outside the boundary layer. Now, you can see this is an aeroplane. The force acting in the forward direction is the thrust force. The force acting which is in the downward direction is obviously the weight of this aeroplane and the passenger inside it, which is the weight. And the force which is acting out to balance this weight, there is a lift force which is acting upwards. That is the reason the aeroplane can fly. All right. Then there's a force which is acting in the backward direction, which is pushing the aeroplane in the backward direction. This is the drag, which will be studying in the further module. So, just for imaginary point of view, you can see, if this all is fluid, this blue color is all fluid. This is the air basically. Fluid is also all right. So basically, you can see in this way, at this point of the airplane, the velocity is zero, because this is the no slip condition. The fluid which is be added may stick to the surface. That air is basically passing through this surface, so we can assume that it is sticking to this surface. The velocity of the air will be zero at this point, and eventually, as we go up, the velocity keeps on increasing up to what? Up to this velocity, whatever will be this velocity. This is the free stream velocity in this way. And if you draw the boundary layer, if you draw the boundary layer, it will be like this is the boundary layer. All right. And these points of the boundary layer are the point at which the velocity reaches the free stream velocity. So basically, what is the purpose of the study of the boundary layer? It gives us the practical insight. What, because while for an aeroplane we need to consider this region only, because we need to see what are the forces which will be balancing the lift and weight, which what are the forces which will be balancing the thrust and the drag. So basically, the purpose of the study is to confine this region only, boundary layer, so that we can balance the forces, and how then only then airplane will fly. Otherwise, it may fall down if the forces are not balanced. All right. One more thing. What is boundary layer thickness? I already told you. This is basically the up to this point. This is the tail. All right. This is the boundary layer thickness. It is the distance measure. You can see this is the distance measure perpendicular to the boundary. This is boundary. It is the distance measure perpendicular to the boundary where the velocity reaches the free stream velocity. See, this is del. How much is del? This is the distance measure from where? Perpendicular to the boundary. This is like this, and the del is measuring in the y direction. This is the measure distance perpendicular to the boundary where the velocity reaches the free stream velocity. But in the standard definition, it does not reach the free stream velocity. It reaches 99% or 0.99 times of the free stream velocity, which is equal to the free stream velocity, but we considered it at, because some of the particle, there's some losses also, like in fluid also, inside the flow we have studied, there's some losses in the pipe. So similarly, outside the boundary layer also, there's some fluid, some 0.01% of the fluid which is sticking to the surface, or there's some other loss. So we do consider that it is the distance measure perpendicular to the boundary where the velocity reaches 99 times, 0.99 times of the free stream velocity, or 99% of the free stream velocity. 99%. Similarly, like Lifebuoy, we don't kill 100% of the jumps. It comes, I think, kills 99.99%. All right. So that is the clearance we usually take. All right. So you can see boundary layer thickness. It is defined as the distance measured perpendicular to boundary or wall where the velocity reaches 99% of the free stream velocity. All right, I think this boundary layer concept is clear, I think. So basically what happened is, as we have studied, as we go, uh, yes, as we proceed towards this edge, towards the trailing edge, towards this point, what happened is the boundary layer increases. See, at this point, this is tail, and it continuously keeps on increasing up to a certain extent. All right. But if we consider a long plate, there are various regions which we have divided. You can see boundary layer along a thin plate. You can see as the this is the boundary layer, this is the boundary layer, right? But what happened is here also the concept of laminar and turbulent flow comes into picture up to a certain extent. Up to the this is the leading edge, starting of the boundary layer. This is the trailing edge. All right, end of the boundary layer. So what happened is, as the fluid flow, you can see the velocity graph is same within laminar flow. You can see this is the boundary layer theory. Boundary layer up to this extent there will be laminar flow. The flow will be along the streamline. You can see these lines, these are along the, these are very simple lines along the flow, streamlines, because it is a laminar flow. Laminar flow is a very streamlined flow. All right, then after a particular extent of time, after x critical value, this is the critical value of laminar layer up to critical value, then there's transition zone in which the fluid gets in a very randomized motion, haphazard motion of the fluid. This is the transition zone, and after completing that transition zone, the fluid become aggressive. All right, so you can see the motion of these particles. These are aggressive mode particles. So basically, this is the region of turbulent boundary layer. The concept is same. Boundary layer concept is same. You can see the graph. The graph will be like this only for the boundary layer. All right, and the velocity projection you can see is same. But if we consider a long thin plate, we have divided the region into three parts. One is the laminar boundary layer, boundary region, then transition zone, and then the turbulent boundary region. Up to a certain extent, there will be the flow of laminar flow, and this critical value you might have studied in pipe also. All right, this is external surface, this is the boundary. But in pipe, what was happening? You can see this was the pipe flow, and the fluid is flowing with velocity v, and it is getting exit at some velocity, whatever. So basically, in pipe, Reynolds number was 2000 for laminar flow, but for turbulent flow, it was 4000. So basically, how we came to know that it is a laminar flow or turbulent flow? On the basis of Reynolds number. If the Reynolds number is less than or equal to 2000, then less than or equal to 2000, then it is the laminar flow. If the Reynolds number is If the Reynolds number is greater than or equal to 4000, then it is the turbulent flow. So on the basis of Reynolds number, we have defined the internal flow, but this was for internal flow, and this case is for external flow. So here also we have divided the region into three parts: laminar, and after a particular extent of time, there will be turbulent region. You can see there is streamline are very smooth, and here you can see the flow is very aggressive or haphazard motions. So this critical value of Reynolds number for external flow is 5 into 10 raised to the power 5. You have to remember this. Please don't get confused. This is the critical value of Reynolds number for up to this value there will be what? Laminar flow. And as we proceed towards this region, Reynolds number is greater than 5 into 10 raised to the power 5. So how we came to know if the Reynolds number is less than or equal to this value, then this is laminar. The flow is laminar. Uh, then the flow is laminar in external flow. If or a plate flow. If the Reynolds number is greater than 5 into 10 raised to the power 5, then it is the turbulent. So you please categorize these two things very clearly. For internal flow, we have different value of Reynolds number. For external flow, we have different value of Reynolds number. So students usually get confused in examination. They used to remember only this thing, that for Reynolds number is 2000 for laminar flow. No, this is the case for internal flow, and these are the cases for the external flow. So the critical value for the internal flow is 2000, and the critical value for Reynolds number is 5 into 10 to the power 5 for external flow. I hope this is clear. So basically, we have divided the region into three parts. And if you see the velocity distribution graph, you can see this graph. You can see this graph. This is basically for the laminar region, and the graph you see is this. This looks like the parabola. I hope this is the parabolic equation. And if you see, this is somewhat the graph of turbulent flow. This is the velocity graph. Is somewhat flatter than this. You can compare these two. The graph for laminar is parabolic, and the graph for turbulent is flatter than this. So basically, this small flattering part is the basically the graph is the logarithmic graph. All right, this question was also asked in previous year gate questions, that the what is the velocity distribution in laminar? It's parabolic. What is the velocity distribution in turbulent? It's logarithmic. Please do remember it, and the graph also. All right. Further, one more thing. There is one layer. This region within the turbulent boundary layer. There is a region within the turbulent boundary layer. This is the region. This is this region. This layer is basically laminar sublayer. Although the fluid has changed its position from laminar to turbulent, but still within the turbulent boundary layer, there is a region within the turbulent boundary layer where the flow is still laminar, but this region is very small. This is basically viscous sublayer. This region only. This is a small part of the region which is still laminar. All right, this is clear. We started from a laminar flow, then there is transition, then obviously turbulent flow. In turbulent flow, the flow is very haphazard and the fluid is behaving very aggressively. But also within the turbulent boundary layer, there is a small region within the turbulent boundary layer where we can consider the fluid is still laminar. But this is a very small region, and up to this very small height, this is basically Dale star. You can say anything, it's simply Dale star, whatever. And this layer is basically laminar sublayer. Please do remember this. So laminar sublayer exists in the turbulent boundary layer. Laminar sublayer, even though the particles are flowing very aggressively in the turbulent boundary layer, but still there is a small region in the turbulent boundary layer where the flow is still laminar. And this small layer is referred to as laminar sublayer. I hope this is clear. All right. I hope, all right. So, you can see, as the depth of the laminar's boundary layer increases, it cannot dissipate the effect of the instability in flow, and hence transition to turbulent boundary layer occurs. All right. So up to this value, up to the critical value, it can support only the streamline flow. After the after this extent, as and how the fluid changes position to the haphazard motion, and it reaches the in the turbulent region. And why this is happening? This is happening because at this point you can see, suppose there's this fluid is coming in contact with this point, this m1 mass which is flowing, but as we proceed in this direction, the mass keep on adding, this fluid mass keep on adding within the boundary layer. this mass keeps on adding within the boundary layer. So basically, this is the reason why the boundary layer is thickness is increasing as we proceed towards the tailing edge. At this point, there is M mass and there's continuous mass addition in the boundary layer. This is the reason this you can see the boundary layer thickness increases. Alright, you can see this is Dale and this keeps on increasing. Why this is increasing? Because there is continuous addition of mass within the boundary layer. Alright. Similarly, for a turbulent boundary layer, there will be more mass. For laminar boundary layer, there will be less mass. Alright. That is the reason you can see clearly from this curve that the boundary layer thickness, this dale is more in the turbulent boundary region and this dale is less in the laminar boundary layer. Why? Because there is continuous addition of mass. So the transition of boundary layer from laminar to turbulent is assumed to occur at critical Reynolds number of 5 into 10 raised to the power 5. As I already told you, this is for external flow. Please do remember. If the plate is very smooth, that even in the region of the turbulent boundary layer, there is a very thin layer just adjacent to the boundary in which the flow is laminar. This is called laminar sublayer. Alright. Even in the turbulent boundary layer, even in the turbulent boundary layer, there exists a small region where the flow is still laminar. This is called as the laminar sublayer. Alright, you can see this part I'm talking about. This is the laminar sublayer and it exists in the turbulent boundary layer. Alright. Other thing, flow inside the boundary layer is rotational and outside is irrotational. This is very important. It was also asked in previous year gate question. Flow inside the boundary is rotational and outside is irrotational. Why this is happening? You can see in the boundary layer there is velocity gradient, there are shear stresses which are acting within the fluid. So due to this reason, the fluid is experiencing a rotational motion with respect to its own axis. Alright, but the fluid outside the boundary layer, as you can see, there is free stream velocity. There is no velocity gradient. There is no shear stress acting outside the boundary layer. Alright, so the fluid is irrotational. So this is important. Please do remember it. Inside the boundary layer, there are velocity gradient, shear stresses. So the flow is rotational. But outside, there is no velocity gradient, no shear stresses. The fluid is irrotational. There is no external force which can act to make them rotate. That is the reason they are irrotational in outside the boundary layer. Secondly, velocity profile is laminar layer is parabolic. As I already told you, the difference between the velocity profile, the difference between the see, you can see this velocity is parabolic and this is logarithmic, somewhat flatter. The velocity profile in turbulent boundary layer is flatter than laminar boundary layer. So the velocity profile in laminar layer is parabolic. Velocity profile in turbulent boundary layer may be taken as either 1/7 power law or logarithm. Alright. What is 1/7 power law? I will tell you. And how will you calculate the I think I lost some points. Yes, this boundary condition. What are the boundary condition? This is also important. This is very important from the numerical point of view in gate. Please to understand it. There are four boundary conditions. What is the boundary condition? At this point, you can see, or you can see at this point. Let us, all right. At this point, x is equal to 0. Since at x equal to 0, at this point the fluid which is sticking to this surface, so u is equal to 0. All right, and u is a different thing. This is a slip condition. Del is 0 at x equal to 0. At this point, you can see this is the starting of the boundary layer. At this point, you can see what is the what is the del? Del value is 0 at x is equal to 0. Since the boundary layer has not yet started to form. All right. So this is condition 1. So simple. At x equal to 0, at the starting, at the leading edge, del, that is the boundary layer thickness, is also 0 because the flow has not yet started. All right. Similarly, at y is equal to 0, if this is the x direction, this is the y direction. All right, this is the y direction. So at y is equal to 0, at this point, at this point only, at y is equal to 0, since the fluid is sticking to the surface, the u is equal to 0. This is the second condition. All right, at x equal to 0, boundary layer thickness is 0. At y is equal to 0, in the perpendicular direction, u is 0 because the it has not yet started to increase. At this point, you can see at y is equal to 0. At this point, u is 0. All right. Third condition. Third condition is at y is equal to del. This is the y direction, and at y is equal to del, as we increases, this is y, this keeps on increasing, this y keep on increasing in the perpendicular direction. When it reaches the value of del, at this point, this is the boundary layer thickness. At this point, when this y reaches the value of del, what is the velocity? This is the velocity of the free stream velocity, that is u is equal to u infinity, as I already told. As we proceed in the upward direction, as the value of y in the perpendicular direction increases, as it reaches the value of the boundary layer, this at this point u is what? U infinity. This is the third condition. All right. Similarly, and at y is equal to del, when the value of y reaches del, at this point, since there is some velocity here, this continuous increase in velocity, and at this point the velocity remain constant. This is also free stream, 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 this is also free stream. U infinity, u infinity, u infinity. So basically there is no velocity gradient once the value of y reaches up to this point. After this point, there is no velocity gradient. As I already told you, we have reached outside the boundary layer, and in that case, du by dy, the change in velocity with respect to this distance is 0. And also, you can consider shear stress is also 0. As I already told you, the fluid outside the boundary layer has no velocity gradient, and there's no shear stresses acting outside the boundary layer. I hope this is clear. These are 4 conditions, very important, and these 2 conditions are most important. At y is equal to del, once the value of y reaches the del, then velocity reaches the free stream velocity. As the value of y reaches the value of del, that is boundary layer thickness, del, then du by dy is 0. Why? Because outside this, there is no change in velocity with respect to this distance. There is a free stream velocity above the boundary layer, and their shear stress is also 0. I hope this is clear. These are 4 boundary conditions, very important. Please do remember them. Please do remember, at x is equal to 0, del is equal to 0. At y is equal to 0, velocity is equal to 0. At y is equal to del, at boundary layer thickness, u is equal to u infinity. At y is equal to del, du by dy is 0. These are 4 boundary conditions. Please do memorize them. It will help in solving the numerical portion. Now let us see the velocity distribution, which I told you. Uh, this is the velocity distribution. This is the comparison. What we have seen in the laminar, you can see this graph, green graph, this is parabolic. while in the turbulent it is much flatter. This you can see. In this way it goes. Further, the boundary layer thickness of the turbulent boundary layer is more in comparison to the laminar. Why? Because as we proceed toward the trailing edge, more and more fluid enter into the boundary layer. So this is the reason the thickness of the boundary layer thickness is turbulent region is more. You can see this is the thickness of the laminar region up to this point, and this is the velocity distribution graph. This is the velocity distribution graph for the laminar layer, and this is for turbulent flow. And for turbulent region, this is the thickness of the boundary layer and turbulent region. All right. I hope this is clear. And you can also see the velocity distribution for laminar, and for laminar flow for this region. For laminar flow, u by u infinity, that is the velocity distribution graph, is basically the parabolic y upon dl. Parabolic is, I think you have studied, I don't know whether you have studied or not. Y square is equal to 4x. These are the equation of a parabola. This is basically quadratic equation. You can see this is the square equation. So this is the velocity distribution for the laminar flow square. All right, because it is a parabolic equation. If the graph is like this and it is a straight line, you already know you have like this value, y is equal to mx. Y is proportional to x. All right. Why? Because it is a linear graph. But if you see, if the graph is like this, y is proportional to x square. All right. Because this is the parabolic graph. So these are some basics. So in laminar region, the velocity distribution graph is parabolic. Velocity distribution graph is parabolic. While in case of turbulent region, you can see uh, the velocity distribution is either 1 by 7th power law or logarithmic. What is 1 by 7th power law? That is u by infinity is y by del e power 1 by 7. This is the velocity distribution for turbulent flow, or you can also write u by infinity log y upon log of del. Both are valid for turbulent boundary layer. So in exam question, don't get confused. Turbulent boundary layer region, the equation of graph is 1 by 7 power law or log or as per the logarithmic curve. While in case of laminar region, it's the parabolic. I hope this is clear. So this was all about the boundary layer and how it gets started, how the formation of boundary layer, what is no no slip point, the point at which the velocity is zero. All right, as we keep the velocity keep on increases, and this is the graph like this, and up to a certain point, as the velocity reaches the free stream velocity, then we receive the boundary layer. And if we connect various point on the boundary layer at which we receive this free stream velocity, we receive a graph like this, and this is nothing but the boundary layer. All right, like this, and you can see the velocity is increasing. Secondly, within the boundary layer, we cannot apply Bernoulli equation because the fluid is not ideal. There is velocity gradient, there are shear stresses. All right. But outside the boundary layer, the fluid is having only the free stream velocity. We can apply easily Bernoulli equation, not an issue because there is no velocity gradient, there are no shear stresses. All right. And what is the boundary layer? It is the distance measured perpendicular to the boundary where the velocity reaches 99% of the free stream velocity. This the velocity is equal to free stream. You can consider up to free stream, but in standard definition, we assume some of the particles stick to the surface or there are some losses. So this is 99% of the free stream velocity. Their boundary condition very important. Four boundary condition. At this point, tail is zero. At this point, since the y has not started yet, u is zero. At y is equal to this point, the velocity reaches free stream velocity. At y is equal to this point, velocity gradient is zero because outside above it there are no velocity gradient. You can see the velocity profile is laminar in parabolic in laminar flow and logarithmic in turbulent flow. So this is the graph of the parabolic equation. Right. Further, as we increase towards the trailing edge, the boundary layer thickness increases. Up to what distance? And up to a particular distance, we will follow the laminar law. That is 5 into 10 to the power 5. This is the critical value of Reynolds number, similar to the critical value of Reynolds number in internal flow. So this is basically the introduction of this boundary layer and what actually is boundary layer, what are the regions we need to study in boundary layer. In the subsequent, in the coming videos, I will be dealing with the types of boundary layer, what are the various losses which occur in the boundary layer, how the boundary layer separates. All right, because there's when there is attachment, there is also separation. All right, so we will be studying that in the upcoming module. So thank you so much for watching the video.